chemist. I'm doing my PhD in the group of Professor Fang at the TU Dresden. We work with molecular functional materials, and I will talk now about 2D materials. I will explain why this can be interesting and what the benefit maybe can be of those materials to solve some energy problems in the future. I'm at the beginning of this development chain, really basic, fundamental science. The world needs more and more energy. It's always rising. We need some other solutions, clean energy. Solutions maybe are fuel cells. Fuel cell need hydrogen and oxygen. How we get this costs as well energy. And for this, these 2D materials can help. 2D materials means as well it's flat. Consider this as this. Large sheets, carbon, flat, has a thickness from one atom layer. And this is stacked. And each of this sheet can consider as one molecule, one polymer. A lot of carbon molecules are connected to such honeycomb structures. When you think this without end, then you get one sheet. When you have this, much more of it, you have a powder. When we have only one layer of this, then it can be a membrane. As a synthetic chemist, we can synthesize this as we want. So this means we can implement some special atoms inside to tune the ability to make oxygen from water or hydrogen. Because on the surface, which has tailor-made properties, we can tune the reactivity of water maybe. This is interesting for me to work on this topic. Since it's really fundamental chemistry, it's a lot of try and error, there's a lot going wrong and a lot which does not work until I have a really homogeneously large area film or layer as a clean material. Now we go a little bit deeper in the material, so we zoom now. When I have it in a glass, it's a powder. My material is yellow, it's just a yellow powder like sand or something, maybe a little bit more fine. When we zoom now, take one layer. And we zoom more, go to the atomic scale. So what we have there actually. So I build up structures which look like honeycombs. In these honeycombs, inside there's nothing. I only have material here on these lines. Here are materials, here are actually atoms connected to each other, and here inside is nothing. And this is as well a very unique property of these materials. They're very porous. Their density is very, very low. That means a lot of gases can be put inside. And this is another property of these materials. You can use them, for example, as carbon dioxide storage. You can put CO2 inside and it doesn't come out again. This can be maybe used as CO2 filter. Of course, there are other structures. For example, squares. It's the same principle. Here we have connecting points and inside is nothing. Or there are a lot more structures, depending on how we build up these materials. And how do we build up these materials? So we zoom a little bit more and check what is these connecting points. Now we have to consider what do we need for molecules to get this. We always have some trigonal connecting points. So we need a molecule which has this geometry, and here some functional groups which can react. So what I'm doing now to get this structure is to take these molecules. For example, I take one of this, I take the second one. Like this, I build it up. By altering the molecule size or adding a spacer, which can have as well different lengths, I can alter the pore size, the density, or tailor-make the volume inside of these materials. So this is one method to tailor-make the material that it has in the end, the properties it should have. The other one is atoms inside. All my material is based on carbon. So it's organic materials, it's metal-free, but we can put inside some nitrogen. For example, specifically only on this side of this molecule, here, here, and here a nitrogen inside a carbon. Now, nitrogen will introduce some different electronic properties. We can low down a little bit the electron affinity, so it gets more electron affine, and we can tune the energy of electron orbitals. We can tailor-make semiconductors, which can be used, for example, in transistors for smartphones. Nobody did it yet, but it's possible. Triphenylamine, and here is a functional group. This is an aldehyde group. If I want to have some other groups here, I can synthesize this in the lab from starting material, from smaller molecules, and maybe introduce here another nitrogen or another core, maybe another benzene ring here inside. How do I synthesize this actually? I just use ampule under vacuum, so I evacuate it, I close it, and then I put it for several days in the oven. I use a solvent which is very bad for these molecules. Only a small part of the molecules is dissolved and react in the solution. Inside it reacts after another. So at first in the solvent dissolved, but at some point when the polymer grows too big, it will precipitate, but then it will go on growing one on another. When we have some oligomers, then it will precipitate very early and react in the solid.
So basically you don't know what you are doing. There is so you have a recipe which says if you combine material A with material B, it will form that, and if you add C, it will remove all the unnecessary things and reform them back to the expected situation.
Short answer, yes. If I follow all this recipe, which is known and which is tested, then yes. But if you change it a little bit, it can go bad.
And how you find this recipe?
It's a lot of try and error, but not too much, because you can expect that some molecules react.
Right.
But you have to tune it a little bit. In the beginning, it's a lot of try and error. You have to make a lot of reactions until you get a good result. We do this because we want to have the material. So at first we think which molecules should react, which reaction do we use for this, which atoms are inside, and then how these atoms influence the reactivity. So then we have to a lot more things where we can tune, like solvent or something. So at first we think of our chemical understanding from the experience we have from other reactions, which conditions we can use, but this does not mean that it will work. So we still have to try a lot. To exchange one carbon atom to a nitrogen atom, this will exactly change the properties of this molecule and in the end, of course, of my polymer. Considering this is graphite, this is in a pencil. There are several methods to get this layer, but in general they stick together. All are with force. For example, in a dispersion, so you put this powder just in a solvent, it will not dissolve. We'll put it in an ultrasonication bath, for example. So then the solvent can intercalate here inside, and in the end it rips off. Or for example, in ball milling machine, you put this powder in a small reactor with some balls, and then it shakes all the time. And through this interaction of the balls with this material, it can delaminate as well. You can build up these materials directly, monolayer. When you want to have a material which is 2D, you have to force the material in this geometry, because it's not natural geometry to have a really high order material. One method is to just use the surface. This will react with this, and then here, and then here, and here, and so you get this geometry. The force here is that you have a surface on which the molecules lay. 1, 2, 3, and so on. Yeah? So like this, it can react just by sticking the molecules on the surface. Kind of a work to try the conditions, but you can end up with a monolayer. So you have really selective layer, a monoatomatic thick layer. Error checking principle. This is one connection point. And this bond can open again. For example, under influence of water or acids, this can reopen, and again we can end up with this amine group and the aldehyde group. This reaction goes in both ways. It can be reversible if you have one layer of a nice 2D material, and then on it starts to react another layer, and it doesn't work out because this group reacts not in this geometry, but for example in this does not fit. You have here maybe some layers when you look from top, and then one like this. So this will destroy this ordering. When this happens, a lot of times you will end up with an amorphous material, because just little defects will destroy your complete ordering, and you won't get another layer here, but you have these cracks and you won't have an ordering. So in the end you will end up with amorphous, non-ordered, non-crystalline material. So in the end we talk about crystallinity. But this group can open, and then you have kind of an error checking process, and again the molecules will align in a manner that they fit inside this crystal, and then they react again. There's another method. You can grow a crystal from organic materials. When you see the molecules are ordered like this, and when you have the functional groups here at the end, you can take just the crystal, make the reaction maybe through heat or through irradiation of light, and they can connect. And then you just have these defined layers. This is another method to get really 2D layers. We don't have a control in this particular reaction at this place, but we have a control regarding solvents, temperature, and reaction time in which the reaction takes place. When you heat it too much, you won't get a result. Or too short, then the crystals are too small, and you will see it, for example, in the characterizations like surface area, that it's much lower. In the end, it's a matter of experience that we know this error correction takes place, and it goes better when we use, for example, as a solvent mesitylene dioxane mixture 5:1, 120 degrees 3 days. So in these conditions, reaction works very well, and in the end, we will have a very highly crystalline, highly ordered material. But what happens inside exactly and how many wrong connections we have, that we cannot say in detail. How do we know that we have exactly this, what we expect, or we have some other stuff, what we don't know? We consider this as the layers, a lot of layers in my material. The simple way of measuring the quality of this material is measuring the surface. And these materials I mentioned at the beginning have a very high surface, a very low density, so it means a very high surface. So inside the pores, when you think the pores here through the layers form kind of channels. So this material has a really high surface, and you can measure the surface area. When you have a lot of layers together, these form a crystal, and you can measure crystalline spectroscopy, like IR techniques, to see if you have the functional groups. So in the end, we need several methods of characterization to see if we have this material what we want. So in the end, when we have solved this puzzle, maybe we have a nice new material which in far future we can use for some energy problems to solve.
Thank you.